Actually, I just started recording again. Let's actually go through the conceptual questions together, and then as time allows, we will also be able to do any of the problems. Sorry, you guys are going to have to stop that, or somebody's going to get hurt. I'm fairly certain it's not going to be me, unless we count my fist. Okay. You may notice as well that the uploaded solutions that I did yesterday actually have some extra because I was doing these when I was too busy and did the numbers in the conceptual questions, and then realized that and said, oh, okay, and then went and did the problems as well. So there's a few extra. So if you get the hankering to do a few extra problems this chapter, you will be able to find them. But let's look at the conceptual questions first. It says in figure 18.8, the grounding wire is removed first, followed by the rod, and the sphere is left with a positive charge. So this is the case where you've got an isolated sphere up here. You had a rod with what charge? Which is on page 541. A negatively charged rod coming in. Okay, and this is grounded. And ground we symbolize like that. We're going to do a fair bit with circuitry starting later this week. That's a symbol for ground. So the grounding wire is removed first. So the rod's brought in. What happens when the rod is brought in?
The charges and electrons go to the ball.
No, we're not touching it. So they're not going to jump through the air to do this.
So just like move it. So if the rod is removed first.
Nope. We're not talking about the rod. I'm just saying. So before we even say that, what charge is on the rod or on the sphere originally? So let's get this stuff together.
You put it in the
I put it in the wrong spot so it didn't recognize. Okay. So right now, what charge would this sphere have? Neutral. Neutral. So it would have positives throughout, and it would have an equal number of negatives. Okay? But now we're going to bring in our negatively charged rod. What happens? Positives don't move. The electrons can, though, and not certainly all of them, but some of them would move. And where would they move to in this scenario? Certainly they'd move over, but yeah, they could get to ground because then they could spread out. So a lot of the electrons, oh sure, I gotta do it one at a, there we are, would move over into the ground. Now we remove the ground.
Why not all of them?
Because most of the electrons, even in conductors, are held very tightly close to the atom. It's only some of the outermost, the valence electrons, that can move freely. And that creates sort of a sea of electrons that flows very evenly. Okay, so now we remove the ground. The ground took those electrons with it. Now, even if we do move this rod, there's no place to get those electrons back from. So the sphere remains positive. Yes?
Why did the electrons move on the rod? Why did they, when you speak?
I was picturing, so the rod is charged, and unless there's, even if it's a conductive rod, if there's no place for those to go, then they just stay there. So in this case, with these parts, group those. If you're holding this, if it's either a conductive rod that you're holding with, say, a rubber glove or a rubber ring around it or something, there's no way for those to flow off. Or if you have an insulating rod, the electrons can't flow regardless. So once you put them on there, they're on there. Like our PVC or the acrylic. They can't really move and get to your hand and flow away anyway, so they stay there. And that, remember, is, what special word did we have for that kind of charge? Static. So they couldn't move. That's what static means. So then you can move this around. That's annoying. And it doesn't really matter. They're just going to stay there. There's no place for them to go. Okay, number 2, it says a metallic object is given a positive charge by the process of induction. That's what we just did here. Induction, remember, means that forced charge on a neutral object. Does the mass of the object increase, decrease, or remain the same? So this object, from the beginning to the end, did it increase, decrease, or remain the same? Why?
Because I lost some electrons.
Decrease because it lost some electrons. What happens to the mass of an object if it's given a negative charge? Increased. Now the key to this is that it does have to be hooked up to a ground like this to allow those electrons to actually move off of it or move onto it. If we start out with putting these back, our neutral object again, but without a ground, and we put this close, we're still going to induce a charge over here. The electrons will tend to move, some of them again, will tend to move to the other side. So this induces a charge just in this area, but the whole thing is still neutral. So that would not change its mass or its overall charge. If you're sufficiently far away, it still looks neutral, and you wouldn't sense it.
Wouldn't also be negative on the other side as well?
Here?
Yeah.
The blues are.
It would be more negative.
But there's the same number of positive and negative charges overall on here, because there's no place, in this example, there's no place for them to go. They just would move to the other side of the object. Yep, Matt.
So could there be a negative charge so big that, like, if there were multiple like electrons on a thing, that they would move so close that they would touch each other?
Electrons, the force gets so big the closer these charges get that they never technically touch and occupy the same space. They just get really, really close to where that force is huge. Yep.
So it's atomic magnetism that keeps us from going through objects?
Yeah, the electrostatic force is what we call that. Yep, that keeps us from going through things because the electrons of our hands get very close to the electrons of the table. And so they never really touch. The collisions that occur between them happen when they get very, very close, and that's what transfers thermal energy. But they never technically touch.
Troy was wondering if you had antimatter protons, right?
Which are, yeah, okay, antiprotons we call them. Okay, let's go back then. Okay, number 3. A rod made from insulating material carries a net charge, while a copper sphere is neutral. The rod and the sphere do not touch. Is it possible for the rod and the sphere to A, attract one another? So you've got a neutral conducting sphere, copper sphere, and a rod with a charge. Would, just doesn't matter. It's insulating, it says, but it wouldn't actually matter. Would they ever attract one another?
Yes.
They could. Under what circumstances would they attract one another? If the sphere is neutral, and let's say this rod is negative, would they attract each other?
Yeah.
Right here, right? What if this was positive? What would happen here? The electrons would move to this side. So electrons from all over would move over here. Remember, protons can't move. They're stuck in the lattice of that, so in the nucleus, so they're not moving around. But yeah, this would still attract anytime that's charged. One last question. Would they ever repel each other?
No.
Can't make them repel. Yes, Matt.